Our next section is section 4.2. In section 4.2, we're going to be talking about a totally different type of function. It's called exponential functions. Now, an algebraic function or a quadratic function looks like this, where we have y is equal to x to the second. A cubic function is x to the third. What an exponential function is, an exponential is actually where the x is the exponent. So we're switching the x and the 2. So let me show you a little bit of how the graphs are different. Okay, so I'll graph our quadratic function in green. So it's 0, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. And negative 1 squared is 1, and then we could just kind of mirror these over. You know, something like this. That's what a quadratic function looks like. Now let's look at how an exponential function is a little bit different. 2 to the 0 is 1. 2 to the negative first is 1/2. 2 to the negative second is 1/4. So on this side, as long as we raise 2 to any power, it's never going to be negative. So it looks like we have an asymptote. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. So it looks similar. But what happens after 2 to the fourth? So when x is 4, x squared is 16, and 2 to the x, 2 to the fourth is 16. So they're the same at 16, but past that, like what about 5? 5 squared is 25, but 2 to the fifth is 32. And at 6, 6 squared is 36, but 2 to the sixth is 64. So you could see that this is growing much faster than x to the second. Let me show you what you need to know about the graph, or the parent graph, of an exponential function. In general, the graph looks like we just drew. The y-intercept is 1, and then it just kind of shoots up. I would like you to remember 3 things about this graph. This is the graph of 2 to the x. First thing is it looks like a hockey stick. You know how we said a quadratic looks like a parabola or a U? Well, this one, let's talk about it as a hockey stick. Second thing I'd like you to remember is that the y-intercept is 1. Has to be, because if you put 0 in for x, anything to the 0 power is 1. And then the third thing is that the x-axis, or y equals 0, is an asymptote. The graph will never cross this line. You can't raise 2 to a power to get a negative answer. Okay, so that's our graph. And let's talk about something a little bit different, and then we'll talk about transforming these graphs. Let's just quickly go over our properties of exponents. One of the properties is the 0 power. Anything to the 0 power is 1. That's why our y-intercept is 1. We also have the reciprocal property. It says if we have a negative power, we're going to write 1 over x to the m. That's why 2 to the negative second is 1 over 2 squared, or 1/4. And then we have x to the m over n, the rational exponent property. Remember, we said there's two ways to look at this. One way is the nth root of x to the m. Another way to look at this is the nth root of x to the m, like that. So let's evaluate if f of x is the exponential function 9 to the x power, just using our properties. What's f of negative 2? Well, 9 to the negative second would be 1 over 9 to the second, or 1 over 81. We don't use decimals in case, you haven't been picking up on that. Usually everything's in fractions. What about f to the 0? What's the y value when x is 0? Anything to the 0 power is 1. And then the last example, what about f, f of 3/2, which means 9 to the 3/2 power, which means the second root of 9 to the third, or the second root of 9 to the third power. Now 9 to the third, I can't figure that out without a calculator, but the second one I could. Square root of 9 is 3, and 3 to the third is 27. So if we have either option, I'm going to pick the second one. That's a little bit easier for me to do in my head. So now let's talk about how to graph exponential functions. So in order to talk about this, remember when we first started talking about graphing transformations, we had like absolute value we were working with. That was our parent graph. So what we're going to actually do is, instead of talking about absolute value, we're going to talk about an exponential function. So like a times 2 bx plus c's on the inside, and then we have plus d on the outside. So let's go over what these do again. D is going to move the graph up and down. If d is positive, it goes up. Negative, it goes down. So I'll write that over here. If d is positive, the graph goes up. If d is negative, the graph goes down. And what about c? C is going to move the graph left and right. It's positive, it goes left. Negative, it goes down. And then we have A and B. And A and B were a little bit tricky. I'll start with A. If A, ignore whether it's positive or negative, but if A is bigger than 1, this is a vertical stretch, which looks like the graph gets narrow. This is similar to if B was also bigger than 1. I'll try to move this over. Need a little bit more room. If the absolute value of B was bigger than 1, this would be called a horizontal shrink, but it would have the same effect. The graph would get narrow. If the absolute value of A was less than 1, we call that a vertical shrink. The graph would get wider. That has the same effect as if B was less than 1, except we would call it a horizontal stretch. If A was negative, we would reflect over the x-axis, and if b was negative, we would reflect over the y-axis. One other thing I just want to point out with b is, just like before, you always want to factor out b first. That way it gives us a better idea of if it moves left, right, and by how much. So you always have to make sure that you factor out b first if that is there. So let's do some examples. What I'm going to ask you to do is graph and state the domain and range. Okay, so let's take a look. First one says f of x is equal to 2 to the x plus 1. Okay, well, our parent graph of 2 to the x would look like this, with the asymptote along the x-axis. Putting a plus 1 here moves the whole graph up 1. So our y-intercept that was 1 is now going to be 2. You're moving everything up 1, right? So our y-intercept, I mean, you could even put 0 in for x if you want. You get 1 plus 1 is 2. The horizontal asymptote was a 0, but if you move it up 1, it's going to be at 1. So as far as what our domain is, the domain could be any number. But as far as our range, well, looks like the graph, the y values, it doesn't start at 1. It starts like any number after 1, and it goes up for forever. So that would be our first example. How about a problem like this? Let's say f of x is equal to negative 2 to the x plus 1 inside the power. So the power is x plus 1. Okay, so let's walk through this. This is normally what 2 to the x looks like. Now the plus 1, whenever we're trying to figure out what order everything happens in, we follow order of operations. So with order of operations, we have Pemdas. We always start from the inside and work our way out. So the first thing that happens, if I told you x was 1, the first thing you would do is you would add 1, right? So we're going to move this graph to the left 1. Now the negative in front is going to reflect over the x-axis. So we're going to take this graph and we're just going to actually mirror it over the x-axis. So it looks something like that. So let's go through the y-intercept. Well, let's put 0 in for x and see what happens. We get negative 2 to the 0 plus 1 power, or negative 2 to the first, which is just negative 2. That's actually our y-intercept, so I drew this a little too steep. Something like that. Now our horizontal asymptote. It was at 0, right? And that only changes if you move the graph up or down. We didn't do that here, so the horizontal asymptote is still 0. The one above it, the horizontal asymptote, we moved everything up, so it went up to 1. Now our domain, we could plug in any number we want for x. So that's going to be negative infinity to positive infinity. Our range, well, it looks like if the horizontal asymptote is at 0, looks like we don't have any, the highest it's going to be is 0. But it actually goes down for forever. So that's how we would write the range for this graph. The left number is always the lowest, and the right number is always the highest. How about if we had this? F of x is equal to 2 to the negative x plus 1 power. Well, we do have a number in front of b, so the first thing we have to do is let's factor out that negative 1. And we can see that this graph goes to the right 1, and this is going to reflect over the y-axis. So this is how we draw something like this. This is what the graph would normally look like. If we reflect it over the y-axis, it would look like that. And then if we move it to the right 1, it would look like that. So when I'm grading this, I would expect you to list all these transformations, and it happens in that order. It reflects over the y-axis, and then it gets moved to the right 1. Another way you could look at this, I don't recommend doing it this way, but look, we can move the original graph to the left 1, and then reflect it over the y-axis. So it's a little bit tricky that way. The way that I would recommend that you do it is factor out the negative, reflect the graph, so spin it around, and then move it to the right 1. So let's answer our questions. What's the y-intercept? We'll put 0 in for x, and you get y is equal to 2 to the first. So it's just 2. Your horizontal asymptote, we didn't move the graph up or down, so it's going to stay at 0. Our domain is going to be from negative infinity to positive infinity. And our range, it looks like the lowest y value is going to be 0, and it's going to go up until infinity. The last problem we have for this type of example is, what if I asked you to graph f of x is equal to 1/3 x? Now in general graphs, exponential graphs, they get steeper as the number gets bigger. So like this is what 2 to the x looks like. This is what 3 to the x looks like. This is what 4 to the x looks like. And I'm sure you get the idea. It gets steeper as our base gets bigger. But what about 1/3? Well, 1/3 is really just 3 to the negative first power, right? If we use the reciprocal property. So we're really just graphing 3 to the negative x. Well, 3 to the x would look like this. But if you put a negative inside, it reflects over the y-axis. That's what the graph of 3 to the x would look like. Our y-intercept, if you put 0 in for x, you would get 1. Anything to the 0 power is 1. And your horizontal asymptote would be y is equal to 0. The domain for this graph, we could plug in any number you'd like. And our range, looks like the lowest it goes is 0 up to infinity. Let's talk about how to solve exponential equations next. One way that we could do them is to write as the same base to a power. And then what we could do is we could set the powers equal to each other. So let me show you a few examples here. And the directions are going to be to solve. So what if I asked you to solve 2 to what power is 4? Well, clearly 2 to the second is 4, right? Well, we could also write 4 as 2 to the second, and then just set the powers equal to each other. X would be 2. So what about if we said 3 to the x power is 1/9? Well, let's try to get the same base. Instead of writing 1 over 9, I'm going to write 9 to the negative first. And remember, 9 is just 3 squared. So we get 3 to the x is equal to 3 to the negative second. So x would be negative 2. And then the last example here, what if we had 2 to the negative x is equal to 1/8? Well, let's use the reciprocal property. And we know that 8 is 2 to the third. So we get 2 to the negative x is equal to 2 to the negative third. So negative x is negative 3, or x is 3. They're pretty easy. I'm sure you guys can handle that kind of stuff. All right, and let's move on to something else. I'll teach you a new key on your calculator. The number e. So remember, on your calculator you have a pi button, and pi is about 3.1415 whatever. Some people think pi means 22 over 7. I mean, that's close, but it's not exactly what it is. It's an approximation. What pi actually means is if you take any circle and you take their circumference divided by the diameter, you come up with that number, 3.1415. So here's a circle, here's the diameter. If you take a rope or a string and you measure it out to that diameter, you'd get 1 diameter, 2 diameters, 3 diameters, and a little bit more. That would be like 0.1415 diameters. So that's where the number pi actually comes from. The number e has a little bit more of an interesting background. The number e actually means the sum from when n is equal to 0 to infinity of 1 over n. So you probably have no idea what that means. E just stands for sum, and n is going to start at 0, and we're going to go up to infinity. I just drew a factorial symbol. Factorial just means you multiply all the preceding numbers times the current number. So let me just explain. This isn't critical that you know what it is, but I just want to make sure my instruction's complete. So this would be 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and this number just keeps repeating for infinity. Now 0 factorial by definition is just 1, so you have 1 over 1 plus 1 over 1 is still 1 plus 1 over 2 factorial means 1 times 2. 3 factorial means 1 over 1 times 2 times 3. 4 factorial means 1 over 1 times 2 times 3 times 4. Bottom line, e means about 2.718. Okay? So we're going to be using that in the next section when we talk about logs. But for right now, it's important that you just know that e is just another number that we're going to be working with. All right? E actually comes in, if you ever heard of an expression called a natural log. That's a logarithm with a base e. And what we're going to be talking about in the next section is we're just going to be talking about how to graph e to a number, just like everything else that we've been doing. So let's get into some examples. What if I asked you to graph y is equal to e to the x? Well, remember what e is. E is just like 2.7. It's just a number. E is just a number. So the way we graph any number to the x power, so it looks like that. It's an exponential function. The y-intercept, if you put 0 in for x, anything to the 0 power is 1. So this graph is also 1. And our horizontal asymptote is still the line y equals 0. One more example like this. What if we had y is equal to e to the x minus 2 power plus 1? Okay, well, it's going to be the same graph, just move to the right 2 and then up 1. So let's see what this looks like. This is a normal exponential function. We are going to move that to the right 2, and then we're going to move it up 1. Right there. So we did move it up 1, so our horizontal asymptote that was usually at 0 is now going to be at 1. And let's figure out what the y-intercept would be. We're going to have to use our calculator to do this. We're going to put 0 in for x. And we're going to type in e to the negative second power plus 1. So the E button is by ln. I think we talked about that a little while ago. So you're going to hit, if you got a TI-30X2S, you would hit second ln. Or if you have another type of calculator, just go to the log menu. It's probably with all the other logs, and you're going to type e to the negative second, and then hit plus 1. And I'm getting my y-intercept. It's a little bit more than 1. It's 1.13 or whatever. Okay, and that's how you graph an exponential function. The domain for this looks like the lowest it goes would be our horizontal asymptote up to infinity. And our range, or actually, I'm sorry, I misspoke. That would actually be the range. So the range, the y values, the lowest it goes would be 1 up to infinity, but we could actually raise e to any number we want. Okay, let's solve an equation with e. E to the 3 minus x is equal to e to the third to the negative x power. I mean, this looks kind of complicated, but it's really not. It's just like the problems we did before. If we have the same base, we could set the exponents equal to each other. So power to a power, remember we multiply. And we do have the same base, so we could just say 3 minus x is equal to negative 3x. Bring the x on the other side. And we could divide by negative 2. So we get x is equal to negative 3 over 2. And then the last topic I wanted to talk about in this section was fractional exponents. And I'll say the directions were to solve x to the 4 thirds is equal to 81. We have a couple different ways we could do this. One way we could do it is we can convert to radicals. I would not recommend doing it that way. The other way we could do it is just raise to the reciprocal power. That way is a little bit faster. So I'll show you both techniques. So this would be the third root of x to the 4th is equal to 81. So what we could do is we could cube both sides. It's going to be a massive number. I'm not going to know what that is. So 81 to the 3rd is 531,441. Then we're going to take the 4th root of both sides. And we get x is equal to the 4th root of that huge number is 27. But if we're raising x to the 4 thirds power, what could we raise both sides to get that to be x to the 1st power? Well, how about 3/4? Then they would cancel, and you just get x is equal to, well, the 4th root of 81 I know is 3, and then 3 to the third is 27. So I prefer doing it that second way. Do one more just to make sure you understand what we're doing here. So x to the 3/2 is equal to 27. So I'll show you two techniques. You can decide whatever way you prefer. First technique, we could write the square root of x to the 3rd power is equal to 27. So let's take the cubed root of both sides, and we would get just the square root of x is equal to 3, and then we could square both sides and get x is equal to 9. Or, once we get x to the 3/2 power is equal to 27, we could raise both sides to the 2/3 power. It's the reciprocal, so these cancel. You just get x to the first when you multiply power to a power. And the cubed root of 27 is 3. 3 squared is 9. So you can see we get the same answer no matter which technique we do. One thing I just want to point out before we close out today, or at least for this section, is whenever you're dealing with radicals, you want to make sure that you check for extraneous solutions. And we said that this happens a few times. One time is if we have rational equations, you want to make sure that you never have the denominator equal to 0. Another time this happens is with absolute value equations. And then a third type is with radical equations, because it's possible once in a while you could wind up with taking the square root of a negative or getting a square root is equal to a negative number. So I'm just going to double check and make sure our answers work. If we plug this in here, 27 to the 4/3 would be 3 to the 4th or 81, so that works fine. And with 9, if we were to do 9 to the 3/2 power, the square root of 9 is 3, 3 to the 3rd is 27. So we're good here, but just so we're complete, you want to make sure you check for extraneous solutions if you have any of those three types of equations.